So, here is the second most famous equation in the world, force equals mass times acceleration. We did quite a bit of work with this. Now it's time to talk about this, force. And if we're going to talk about force, that means we have to talk about vectors. That gets us to page 50 in the book. There are two types of measurements that we use in physics. They are scalar measures Scalar measures, they indicate magnitude only. Number two, vector measures. They indicate magnitude and direction. All right. So some examples. Under scalar measures, we have mass, length, speed. Okay. All we care about in these cases is how much. That's it. Under vector measurements, force, displacement, velocity. Is it splitting hairs? Yes, it is absolutely splitting hairs. It's physics. Force, remember, that's the difference between mass and force. Okay. We've talked about that before, the difference between mass and weight. Okay. Length versus displacement. Okay, context is going to drive a lot of this. I can say that the distance from here to here is 2 feet, and the distance from here to here is 2 feet. The distance from here to here is 2 feet. Who cares? It's 2 feet. All right. On the other hand, if I was to jump on this table and favor you with my rendition of the funky chicken, and then I moved 2 feet in that direction, it would be all the more entertaining. Similarly, speed versus velocity. If the cop pulls you over for doing 65 and a 35, it doesn't really matter whether you're going north, south, east, or west. It's irrelevant. If, on the other hand, the cop pulls you over for doing 65 miles per hour northbound in the southbound lane, then direction is certainly relevant. All right, so you have to keep your eye on the ball with this stuff. All right, so at the bottom of the page, since vector measures include the component of direction, then that component must be taken into consideration during calculations. All right, so we're going to have to account for direction when we do our arithmetic. Next page, page 51. We are talking about force after all. A way to think about force is to think of bungee cords. Now, recall, we defined force as a push or a pull, or that which affects motion, but let's just keep it simple, a push or a pull. So we'll think about bungee cords. So let's say I have a nail driven into the board here, and I attach a bungee cord pulling in this direction, 5 pounds, and a bungee cord pulling in this direction, 5 pounds. Now, how are we going to indicate direction quantitatively? Well, what we're going to do is we're going to go back to high school algebra. You might remember doing this. 0, 90, 180, 270, and this is also 360. All right. So we'll use that to indicate our directions, all right? So now we can say that this is 5 pounds at 0 degrees. This is 5 pounds at 180 degrees. And what would be the net force if you combine them? Well, the answer would be 0. 0 pounds. Okay? And no direction. It would zero right out right there. Okay? What if, on the other hand, I had, say, 3 pounds, 0 degrees, 5 pounds, 180 degrees. The net would be 2 pounds at 180 degrees. Okay, just think of bungee cords. All right. Well, what if we had bungee cords pulling in the same direction? Well, I would indicate it this way. £5, 0 degrees, 5 pounds, 0 degrees. The net, in this case, would be 10 pounds at 0 degrees. Now, this one throws some folks. That's been my experience, so let me try it this way. Let's say each of these dry erase markers weighed 1 pound. So if I put one dry erase marker in my palm, that would be 1 pound of force at 270 degrees pointing straight down. And I add one more. Now I get a grand total of 2 pounds of force pointing straight down 270 degrees. It's nothing more complicated than that. Okay. So at this point, you should see the range of net forces, or what we call the minimum maximum. You may have heard that term, minimum maximum. So if I had, for instance, 2 5-pound vectors of force, what's the most I'm going to get out of them? Well, that would be 10 pounds. What's the least I'm going to get out of them? 0 pounds. If, going back to the first example, I had 3 pounds, 0 degrees, 5 pounds, 180 degrees. And if I pointed them in different directions, what would be the most I could get? Well, I could get a grand total of 8 pounds. What would be the least I would get would be 2 pounds, all right? So that would be the range. Okay, next page. Page 52. Okay, example 2. 2 bungee cords pulling at a 90-degree angle relative to one another. So that would be something like this. Let's say I got 5 pounds of force like so, 5 pounds of force like so, 5 pounds, 0 degrees, 5 pounds, 90 degrees. All right. What would be the sum total? Well, instinctively, you might think it would be something like this. And you'd be correct. But how much is that? You know, a way to think about that is, think about Dennis the Menace. What does Dennis the Menace have in his back pocket at all times? His slingshot. So just imagine, Dennis the Menace pulling back on his slingshot. Okay, so that would kind of represent what's going on here. But how would we quantify that? Well, the solution is to do what's called a head-to-tail schematic. Here's how we do these. We draw the horizontal vector first. And then I'm going to take this vertical vector and I'm going to move it over like so. Now I'll draw a diagonal, or more importantly, a hypotenuse, like so. That is called a resultant. This is called a head-to-tail schematic. Head to tail. All right, so the sum of these two vectors is called a resultant. So what would be the value of that? Well, we could use Pythagorean. Remember, a squared, if this is side A, and if this is side B, this would be side C, then we would say that a squared plus b squared equals c squared, which is 5 squared plus 5 squared equals c squared. And therefore, c will equal the square root of 50. .071. £7.071. And simply because we can readily see what the geometry of this triangle is, we can quickly deduce that this is 45 degrees here, 45 degrees here. Okay, so the resultant would be 7.071 pounds at 45 degrees. Well, that's great as long as everything is nice and neat, but what if instead of 5 pounds, this was 3.2 pounds, and instead of 5 pounds here, it was, oh, I don't know, 6.37 pounds. How would we figure out the angles then? Well, it wouldn't be with the Pythagorean. The problem with the Pythagorean theorem is that it solves magnitude only. It solves magnitude only. It doesn't tell us direction. So we need something else. And we'll pause here and we'll get on to the solution to that in the next video.